There you go. Okay, thank you. Good morning, everybody. My name is Carlo Zanchetta, and I'm presenting the first part of a project that is going to be developed by me, Professoressa Rossana Paparella, Martina Giorio, and Maria Grazia Donatello. The project regards the definition of BIM-based rating of urban and architectural surfaces to refine solar and potential analysis, and it is based on the interest in activating an urban model of the university asset. University of Padova has an asset of almost 650,000 square meters. 80% of which is has a landmark interest, so we have some problems in generating energy and keeping the cultural interest of the whole asset. The presentation is based in this chapter, so first part, the background related to the motivations that led us to develop this project. Then the main part, which is the definition of the state of the research and definition of the methodology, and then the first experimentation in activating this kind of models. So in the end, the conclusions and future work. So first of all, regarding the background given to the vast interest in supporting our sustainable development, there is a vast interest in definition of solar potential of buildings, and this generates an investment in solar potential simulation tools. On the other hand, there is the necessity to activate public policies to manage energy production, so not based on the private approach, but on large assets, public assets. So this generates the necessity of using urban models more than building models. So the principles of solar potential analysis, as stated in previous research, are quite simple. So starting from the weather data and using the geometry of models, simplified or detailed models that we can get from different data sources, we can obtain the irradiation potential, and related to the irradiation potential, we can calculate the ideal solar potential. So the first problem is that starting from urban simulation with simplified analysis of the solar potential, we are assisting to a significant reduction in the calculated value when compared to the actual energy production after installation. So the problem is that solar potential tools generate an overestimation of the solar potential. On the other hand, urban solar potential simulations need a reliable information base that should stand on detailed representation of buildings, which is not available at the urban scale. So this moves us to the use of detailed BIM-based simulations. But the problem is that detailed BIM-based simulations are not available at a preliminary phase, nor implementable in urban energy models. So there is a lack of information which affects the possibility of following this path. On the other hand, the use of less conventional surfaces such as loggias, balustrades, and so on allows more energy to be generated inside the urban context where high energy demand is concentrated. This is particularly related to the fact that this research we are going to develop is developed in partnership with a colleague from Trondheim University, and there are huge differences in irradiations from Mediterranean area and Norway area. So because of that, our interest is mainly on the roofs. Instead, Professor Lobaccaro's interest is mainly on facades. So this focuses on the interest on working on less conventional surfaces. On the other hand, unconventional surfaces again need reliable information base that should stand on detailed representation of buildings. So once again, we should follow the path of BIM-based simulations. Unfortunately, extend attention to entire neighborhood to consider cast shading elements need to be developed. So the necessity to model neighborhood buildings and trees and infrastructures to analyze cast shading elements push us to the following of urban models and the attention to urban scale because we need to activate smart grids and public authority-driven energy policies leads us to the activation of urban models as stated in literature. And once again, the public authority strategies require very large analysis that are not affordable using BIM-based models. And in the end, the weather data is available at urban scale. So once again, we have to work at urban scale. So it seems that we are losing the possibility of capitalizing the properties of BIM models on one hand and urban models on the other. Our approach is to define a process using enriched urban building energy models. So we started thinking about modeling detailed models, some detailed models based on our knowledge of those models, and then to define two factors. One factor is the transformability rate, and the other factor is the glazing factor, in order to refine the solar potential. So this is more or less the methodology schema. The first step is to collect urban data. As we will see later, we will get it from the OpenStreetMap database, and then to refine those data, we will use Java OpenStreetMap tool, and then to collect the data in Urbano, which is part of the Grasshopper collection working on Rhino. Then to implement the Energy Plus weather data inside Ladybug to generate the simplified solar potential. On the second hand, by getting the building data coming from BIM-based model, or maybe even from CAD models, because it doesn't affect the particular information we need to get, which is the percentage of glazing of the facades, we can simulate the real solar potential. Once we define the real solar potential, we can get the transformability coefficient as a ratio between the real and the standardized, moderated using the percentage of glazing. In the end, this leads us to two processes. One process is the definition of typologies or archetypes. And using archetypes, we can avoid the use of detailed BIM-based models. On the other hand, the second possibility is to generate new tags for urban database in order to populate them and reuse this knowledge in other simulations. So the problem is, in the end, the availability of urban and weather data, the calculation of building data in terms of glazing factor, the calculation of building data in terms of transformability of building facades and roofs, and most of all, which is my and our main interest, the interoperability of all of these data. So the experimentation regards, as I mentioned, part of the building stock of the University of Padova. This is the identification of the buildings. In particular, we focused on two very different buildings. One is the office building, and the other one is the labs for experimentation. And as I mentioned, after having analyzed the literature, we found that the most reliable data source could be the OpenStreetMap project, given the fact that it has a huge history in updating the data, and it has the availability of data without legal or technical restrictions. The problem is that it is not an ISO-mapped international standard like CDGML, but it has a well-defined structure that is easy accessible. So, in our opinion, OSM meets the ISO standards in terms of standardization and information and interoperability. The data types of OpenStreetMap are 4. So we have nodes, ways, which are more or less collection of nodes, and relations, which are collection of tags, which define and specify the kind of nodes that populate the ways. And the tags are the descriptions of those nodes. So using tags and referring to the ways and the polygons, we can generate a 3D urban model. But our 3D urban model most of the times is wrong because the available database is highly affected by, let's say, it's highly affected by limited information. 3% of 544 million buildings have the height tag. So what we analyzed was the possibility to intervene directly on the database, again using open formats, and we found a good result using Java OpenStreetMap project in which we can intervene by adding some tags, correcting the tags, and then generating the models, the right models. As you can see, sorry, I turned back. As you can see, the lab building is higher than the office building, so clearly this is totally wrong. Okay, so in the end, we activated the simulation, so we could generate the simplified solar potential and the real solar potential, and then generate the data, and then express the data referring to the building ID. We added the transformation coefficient, the solar potential real, the percentage of glazing, and the definition of the archetype in order to republish this XML into the OpenStreetMap database using Java OpenStreetMap. So the result gives us a general solar potential drop of more or less 20%. But what is interesting, for example, if you pay a look to the roof of the offices, we have an increase of the solar potential because it has a particular configuration that demonstrates the possibility using unconventional installation approaches of photovoltaics to generate more energy than what it is estimated using the simple solar potential. Okay, so in the end, we had good results regarding BIM data because it ensures full interoperability. I apologize for the fonts. Full interoperability for geometry and information standardization, and full standardization because we refer to IFC data model. Instead, talking about GIS data, we have full interoperability because, of course, we use standardized file formats, but no standards, and this is in our for me, it is the worst problem that we are facing. And in the end, talking about solar potential simulation, we have good reliability of detailed models. Future work is the definition of glazing and building height, not manually, but based on image recognition, and the assignment of archetype types based on artificial intelligence. Thank you for your attention.